First of all, welcome everybody to this presentation on PartFinder. My name is Rainer Vogt. I'm the Managing Director of Optonic. And yeah, today I would like to introduce you to a new software product. So let's start here. So the product is called PartFinder, and it's a pure software package to locate objects in a point cloud captured by an Ensenso camera. So as you see here on the right, we can go from point cloud to located objects. And the objects themselves are given as STL or PLY model files. So these are all predefined geometries that we try to locate. Why do we want to do this? Lots of applications need to know positions of certain workpieces, or even the trays and the containers of the workpieces need to be located. The classical region here is, of course, bin picking and palletizing, depalletizing applications, where you want to pull out the workpieces, the unsorted workpieces from a container, and either feed them into a machine or put them onto a conveyor belt or similar stuff. This is by far the biggest application area for PartFinder, and the one that we are currently also testing it a lot with. But of course, there are different other potential applications. For the more complex ones, there's all kinds of manufacturing or assembly applications. When you want to put two pieces together, you need to locate them, and then you can actually assemble them together. Or there are applications in the machining area where you want to grind objects, welding, casting, anything like that. And on the more complex side, also defect checking, because if you have located the object in the point cloud, you can also build difference volumes on the object itself to check for completeness and so on. Why would you want to use PartFinder in order to locate objects in point clouds? First of all, it's developed and optimized to work with Ensenso cameras. We derive certain parameters from the camera geometry and from camera configuration. And it's also integrated into the Ensenso SDK to be used easily when you're using Ensenso devices already. Of course, then we would want to provide a very quick preparation and search process. And this one is maybe even more interesting. PartFinder is designed to use all available data queues in order to locate the object. And this is especially important when you have certain difficult parts, difficult lighting situations. So here we use texture information and depth data over all the steps from coarse to fine-grained search and position refinement. This all uses all data queues available. And if you're in the field, I guess you have encountered these situations. You have certain difficult parts, especially ones that are self-similar to some extent or have similar orientations. This is one thing that PartFinder is designed to correctly resolve. And then last but not least, we paid attention to have the whole algorithm work reliably on all kinds of surface geometries. There's, of course, complex geometries like the part shown here, which has all kinds of surface orientations, lots of smaller 3D details, features, and so on. But there's also simpler parts. You might have boxes or sheet metal parts that have only one planar surface that you can see in the camera and so on. These parts might look simple, but especially algorithms that deal only with 3D data have quite some problems locating these accurately. And what's even more is we can also handle textures. This I will talk a bit about later on. So how does the location process in PartFinder work, or what does it do internally? We all start off with the CAD model first. So we have this predefined geometry. We load an STL file or PLY file. And then PartFinder generates really 2D templates from this. And yeah, so basically we render the object from all kinds of orientations. And after that, we can throw away the CAD model again, because now we have our template-based representation of the object. And then we take a camera and capture a point cloud of our scene. And yeah, now you have here the depth data from the scene and the texture data. And this we feed into the search algorithm, which basically, roughly speaking, just convolves the depth template and the texture template with the two layers that we have. So it basically compares all image parts, and then it generates good locations and poses for this. Then, which is not shown here in this picture, but there's a pose refinement step afterwards. And then finally, we output the object poses, which will then nicely fit your point cloud. On the template creation process itself, you can already influence quite some some search behavior. So here I have a few more details about this. Generating the templates is actually a pretty simple process. We you see these small camera parts here, and this is our loaded CAD model. And what happens now is we have a certain discretization, and we generate views of this CAD model from all different viewing angles. So here is one representative viewing angle like here. And of course, this is not completely sufficient, because if we want to have a true template matching, we also have to consider orientations in this viewing angle. So in the end, we will end up with roughly 500 to 5,000 of these templates. And each view includes depth information, texture information, and the boundaries of the object from this view. Of course, you can imagine that having 5,000 images of this object and trying to search this in camera data is probably not very efficient, because that's way too much data. And so there's a data reduction process that's happening during the template creation. So the depth data is subsampled by a automatically derived factor. Of course, you can always influence these things, but in general, the automatic settings are fine. And so the depth layer is subsampled, and the same we do for the texture layer. We subsample the texture and boundary information in order to only have a very sparse representation of each of these templates. This whole template creation process is actually already useful in order to influence your search results. In the simplest case, you can just sample all the directions. If you have a very a general object which can occur in all kinds of orientations, you simply leave the default, which is generate templates from all directions. But if you have for example, a sheet metal part or something like this, you would not expect the sheet metal part to be standing upright in your bin. This will usually not happen. It will just fall to one of the two sides of the sheet metal part. And so you can tell the template creation to only create templates from the top or from the bottom view of your object. And even more, if you have a rotation symmetric part like the one shown here, you can tell it that it's rotation symmetric around one of these axes and only create templates around, basically off axis. And every rotation along the axis will not change the templates anyway, so we don't need to create them. So why would you want to do this? It sounds like a burden to the user, but in fact, it allows you to pre-select the usable and expected part orientations, or you can even pre-filter what results you will get out. For example, you only have one side of the part where you can pick it. You could simply only create templates from this one side that's usable for you. And of course, it reduces false positives. If you can exclude certain orientations that you cannot use, then you can already exclude this right up front. And of course, it accelerates the matching process, because if you have 100 templates, this works much faster than if you have 5,000. So now that we know what it's doing, I would like to show you the whole operation on one of these data sets here. So this is a simple gear part. I will quickly pull up NX view here. So this gear data set here, where I can show you the basic operation. So this is the setup. We have an X series camera hanging up here, and the bin of these gear parts here in the bin. And so now we can fire up the PartFinder from the tools menu now. And we have to load the CAD model first, which is located right beside the camera data, so it's already here. Okay, so now you can see this is your loaded part. And yeah, in general, you can just leave the default settings here. It just tells you the size again. The models need to be in millimeter size, because yeah, some software tends to export it in meters or something like that. So you have to quickly check that it's correctly scaled. And then you can just click create model, which generates the templates from all the orientations, which is 2,000 templates, if you've quickly seen the message. And yeah, now you're basically done. You can click search, and it will check where it can find the model. And here you are. You have a few findings. Now you might ask, why do we have these missing parts in between? There's a parameter here. After generating a lot of hypotheses where the parts are, these are limited to 30. So if you expect more parts and more results, you might just turn this up here and click search again in order to get a few more results. And now you see that you get much more results out. The results are colored by score. So you see most of them are green, but some on the corners are a bit yellowish, because these have either less 3D points on them, or they are not as good represented in the texture data as the others. You can also click them here and check the results, and they are marked in the 3D view. This is here. And okay, this one in the corner is the worst one, with a score of 66%. But still, it's a correct result returned here. So this is the quick demo of the gear part. And now we can move on. Yeah, tricky parts. Of course, there are different variants of tricky objects. First of all, you might have objects that have some kind of self-similar structure. For example, repetitive geometry, holes that are equally spaced or something like that. And yeah, in general, this poses some problems to the search algorithms because if the repetition distance is not very large, you have quite similar poses that all match the object. So this is definitely difficult. And also you might have slightly asymmetric parts. So for example, this seatbelt buckle here, you'll see that the two orientations, if you turn it like this or upside down, the part is very similar. You have some slightly different bend here. This one is bent down, this one is bent up. But of course, in the 2D view, you will not see this. And also the 3D coverage of points on the surface will be at least somewhat similar in both orientations. And this is also one of the important features of PartFinder, that it implicitly takes care of this, because after generating a lot of potential poses of parts, it allows to generate multiple poses on the same location. So like you see down here, for example, on this part, it will generate one hypothesis with one-sided, with this side bent, and another one with the part bent the other way. And then the refinement process starts, and right in the end, it will decide which of the two potential part poses is the better one. And this actually makes PartFinder resolve most of these difficult things correctly. So this is true for the repetitive parts and also for the symmetric or slight almost symmetries. And we can actually have a look at this very specific example. I'll just fire up the other data set, the seatbelt buckle. And yeah, okay, here we have the scene. Seatbelt buckles as you've seen them right now. The setup is pretty much the same. We have the camera up here. A lot of seatbelt buckles lying on the floor below the camera. And now we will again fire up the PartFinder dialog and load another model. Just this one here. Yeah, so the seatbelt, for example, we could just, to show this feature, we can just use, for example, views from top and bottom, because in this setup, we don't expect our seatbelts to be standing upright on the tip or something like that. So we will just use the top and bottom views. And then we just press create model. So now you see it's generating less templates, only around 1000 now. And we press search again to see what happens. Yeah, now you see you get quite nice results. The parts are actually nicely fitted into the surface, and at least I cannot see any part that it's fitted incorrectly in the incorrect orientation. We have some, at least this one here, which has only a very little coverage, because this front part of the seat belt is highly reflective metal. And you see that this has very little coverage here. You can actually show and hide the parts. So most of this front part here is missing due to reflections, but still it's fitted correctly. So you might want to exclude these not that good matches. So you can just have a look. It's probably this one here. Yeah, score of 64. So we might want to filter this out, turn the score up to 70, which is required. And now the part is gone if we search again. Yeah, so this is a quick demonstration of the capabilities for resolving these similar poses of parts. Good. So now here comes some interesting new stuff. Some of the applications require alignment of the part, not just with the geometry, but with some kind of label or print or whatever, because this might be relevant for further processing of the part. So the pure 3D geometry is just not enough information to correctly orient the part. So if you look at this example, we have this box with equal side lengths here. If you locate this using pure 3D data, you will not be able to distinguish this orientation here with stripes along that way from this orientation. So you will get either the one or the other, but the scores for both variants will be very good. And in the end, you will, if you need the part in a certain orientation, you will need to build up either a second inspection station using a 2D camera, or you will need to use the texture data from the camera to, I don't know, flip the part afterwards. After you've found it, then you bring it manually in the correct location, for example, to the correct orientation. And as PartFinder is template-based, we can actually account for these part textures in the search process itself. So this is, for example, useful for getting the orientation of these stripes right here, for example, in this on this box part. It could be used for aligning the orientation with some kind of labeling or other kinds of textures. I have to say that this is not able to do very sophisticated character recognition or anything like that. So if you want to have some very fine texture details to be matched, this is probably not the right thing to do. But yeah, at least determine the rough orientation using these larger texture structures like the stripes on the parts. This is what it's designed for and what is working nicely. And yeah, if you are lucky, this can actually save you either a separate manual implementation to get the orientation right, or it can even save you a separate inspection station altogether. And this is what we can quickly have a look at. So let's close this one and fire up the boxes. So, okay, you see I've all the time kinds of bin picking setups because this is what we currently have lots of applications for, and therefore we have lots of test data and data sets that we can run on. So this setup here uses an N-series camera, and the bin is down here containing these boxes. Let's navigate down a bit. Oops. So you might notice that these boxes are really stacked tightly together. So here is a small gap, but all the other boxes are really, very tight, so that you can actually not really resolve the gaps between the boxes. Of course, you can resolve them if, for example, you go to higher resolution X-series cameras, or you go closer with the camera and so on. But in fact, we have these separation lines in the texture, and we will see that this actually works in order to locate the boxes. So here's the box model. This model actually includes the stripe texture already. So this does not work with STL files, but PLY files are able to include the texture data. And we want to have all orientations of the box. So we don't want to pre-specify any orientation. And I admit I have some prior knowledge. I know that you have to discretize the templates a little bit with finer resolution. So I preset this here. And there's this check mark here to include the texture information of the object in the templates. So this is what we want to use in order to orient the template correctly to the part. So I take this checkbox. You see that the template count will be much higher now, 16,000 templates, because I chose a smaller discretization. But if we now press the search button, so okay, we don't need 65 parts. Maybe we just, I don't know how many boxes are there. I just set around 30 or 25. That's probably enough. And now you see that we have found the boxes. You see that some of them are still not correct. There's one in between here. If we look from the bottom side, you see that it has stacked one in between. This is what we can resolve by allowing less overlap. Okay, so I have to take the advanced box here, and here's the overlap sliders. So you can basically tell it to not allow any overlap or just a little bit. So we want to have the full object not colliding with anything else, or at least we allow maybe 5% of collision. And maybe we just click again. So now the colliding objects in between are gone, you see. And the boxes are all stacked up quite nicely. So here there are a few ones that are not very good, so we can actually exclude them by increasing the score again. Okay, so now we have only good box findings here, and we can start picking. And as soon as we have removed some of the boxes, the remaining ones will also be found nicely, because then you have visible boundaries around here. So now we can actually cycle through this data set a little bit and have a look at the findings. So here there's one where the box order is already a bit destroyed. And there, it's even more disordered. By the way, I did not actually show you that the alignment between the stripes is correct. Maybe we can take a look at this right now. So if I show and hide the findings, we can actually see that the stripes align with the texture of the camera data with all the instances here. So then we can cycle through. And there's one specific image, don't know where it is, that I would like to show. Yeah, so maybe here is a good one. So you see here, there's a box that's tilted over to the side. So this is correctly located, and also down here where we have boxes sitting next to each other. It has not fitted one of the larger top surfaces into it, because it can actually see the separation line here between the boxes in the texture. So it fitted a box lying on its side into here, which is obviously the correct solution. Yeah, and also here, there's one on the side. And here there's even 2 boxes lying sideways, which are correctly fitted into here. Okay. Let's go back to the presentation. So now let's have a quick summary. So PartFinder, what is it? So first of all, it's a software package integrated into Ensenso SDK to locate objects. So basically, your application then starts on the layer of where you have located objects. So you have the camera, you have located objects, and then your application starts. So it does not do complete bin picking. It simply does the location task for you. And yeah, the most suitable and most close, let's say, application is probably picking and handling applications. Where do you get this? There is an implementation on the currently available Ensenso SDK 3.2, which is online. And there will be a newer release of PartFinder in the 3.3 SDK, which will include the texture matching that I've just shown, apart from other improvements, but this is the major one. And this is probably also important. It has a separate license. It comes integrated into Ensenso SDK, but it's licensed as a separate software package. So, of course, licenses are available via the standard way of contacting your IDS sales representative. And there are also trial versions. So this is probably a good way to test PartFinder on your data, on your objects, and in your whole setup and situation. And yeah, try it out for free. And of course, yeah, what additional resources do we have? There's currently in the online documentation of the API functions that you can use to trigger all the PartFinder functions. It basically separates into 2 major functions, one for generating the model and one for searching the model. And especially in the upcoming SDK 3.3, there will be a lot more coding examples and so on in order to get started integrating the function into your own applications. Yeah, thank you very much for listening. And yeah, have a good evening.